All right, we're going to begin to go over the open book test, Unit 1314 for calculus. We want to first talk about the rules for which a limit would exist and the rules for which continuity exists. Remember that there's three rules for which a limit exists, and that is that it must approach the same thing from left and right as x approaches c. It must not approach infinity as x approaches c, and it must not oscillate between two fixed points as x approaches c. We learned that if a function is continuous, and we know that polynomials, radicals, rationals, and trigonometric functions are continuous within their domain, then if that's true, then to be continuous, we know there's three rules. Number one, the function value must exist at c, the limit must exist at c, and the function value is equal to the limit as x approaches c. And so looking at number one, we know that it's a polynomial function over the set of all real numbers, so it's everywhere continuous. Because we know that it's everywhere continuous, then we know that the limit is the same as the function value. So if we just find the function value, 4 times 2 plus 3, that's going to give us the limit. And so we're going to have 4 times 2 is 8, plus 3 is 11. And so the limit as x approaches 2 of f of x is equal to 4x plus 3 is 11. Any questions on that? Okay. Number two, we have a polynomial function. We have a rational function, and it's going to be continuous over its domain. Now, is there anything that x could be that would produce a 0 in the denominator? Remember that division by 0 is undefined, right? So we'd think about that and say, well, x squared plus 1 equals 0, minus 1 minus 1, x squared equal negative 1, and that's impossible over the set of real numbers. So there's no exclusions in the domain. So this, even though it's rational and even though it has a denominator, there's no possible way to get a division by 0 error. Therefore, this is everywhere continuous. Therefore, the limit as x approaches 3 is the same as the function value at x equal 3. So we're going to replace the x both places with the 3. We'll have 3 minus 2 over 3 squared minus 1. Understand that? Plus 1. Thank you. So 3 minus 2 is 1. 3 squared is 9 plus 1 is 10. And so the function value at x equal 3 is 1/10. It's continuous. Therefore, the limit value is also 1/10 at x equal 3. Any questions on that? Okay. Well, let's look at number 3. Number 3 has a square root. If there's a square root, we know that the thing under the square root cannot be negative. And the thing under the square root is x plus 3. And so we would have to know that x plus 3 must be greater than or equal to 0. The radicand must be a positive number or 0. So we could subtract 3 from both sides, and we could say x is greater than or equal to negative 3. So the domain of that function would look like this. It would go from negative 3 included into positive infinity. So it's not everywhere continuous, but it is continuous within its domain. Well, then we would say, is the target value 6 in the domain of that function? Well, it is. So that means it's continuous within that domain. Therefore, the limit as x approaches 6 is the same as the function value because it's continuous within the domain and x and 6 is within the domain. So we're going to have square root of 6 minus 3 and then minus 5 plus 6. I'm having trouble with my pluses and minuses. Thank you. I'm going to remove this over here where we looked at the domain just because we should have. And so we're going to have square root 9 minus 5, which is 3 minus 5, which is negative 2. So the limit as x approaches 6 of f of x, I'm going to write that, of f of x is equal to x plus 3. The limit as x approaches 6 of f of x is equal to x plus 3 is actually equal to what? F of 6, right? The limit as x approaches 6 was the same as f of 6 because it was continuous within that domain and the 6 was a part of the domain of the function. Okay? Any questions on that? So what we're getting now is two functions, and we'll deal with compositions of functions. So we're saying let's let f of x be 2x plus 7 and g of x be x plus square minus 1 for these problems. Notice that in f of x, are there any domain limitations for f of x is equal to x plus 7? Well, for there to be domain limitations, what two things would we check for? For there to be domain limitations, there's two things we'd check for. A division by 0 situation, which means we'd have to have a fraction, and square root of a negative. And so in f of x, there's no fraction, so there wouldn't be a division by 0 error, and there's no square root. So we would say that f of x is everywhere continuous. G of x has no denominator, nor does it have a radical, so it's everywhere continuous. And so that means all of the composition functions would be everywhere continuous. Okay, we want the limit as x approaches 4 of g of x. Since g of x is everywhere continuous, then the limit as x approaches 4 of g of x is the function value g of 4, correct? So if we plugged a 4 in place of the x in the g function, we would get 4 square minus 1. Understand that? And so we have 16 minus 1, which is 15. So the limit as x approaches 4 of g of x is the same as g of 4, which is 15, because it is everywhere continuous. Therefore, it is continuous at 4. Okay? Likewise, because f of x is everywhere continuous, then we would know that it's also continuous at 4. And so the limit as x approaches 4 of f of x then would be f4. So we would take the 4 and plug it in the x in the f function, which would give us 2 times the x of 4 plus 7, which would be 8 plus 7, which would be 15. It's kind of interesting that they came out the same. Not sure why I made it up like that. Just a coincidence, by the way. Any questions so far? All right. And then we've got the limit as x approaches 4 of f of g of x. Well, since both functions are everywhere continuous, then the composition function would be everywhere continuous. Now we want the limit as x approaches 4 of g of f of x. Now what that means is we're going to take the 4 and put it in place of the x in f of x. So that means we want to find g of F4, right? So we're going to take the 4 and put it in place of x in the f function. We've got to find F4 first. which was our 2 times 4 plus 7, which we already know is 15. So we're going to realize then that we're finding G15. So if we hadn't already known F4, we would have taken the 4 and finding the value of F of 4, which is 15, and then we've got to take that 15 and put it in place of the x in the G function. And so we're going to have 15 squared minus 1. 15 squared is 225 minus 1 is 224. And so the limit as x approaches 4 of g of f of x is 224. Any questions on that? Okay. Number 7. Number 7. We'll do one more and then we'll stop. We want the limit as x approaches pi over 2 of sine x. Sine, recall, starts at 0. It goes up, down, up, down, up, down, down, up, down, up, down, up. It's everywhere continuous. Therefore, it is continuous at pi over 2. Therefore, the limit as x approaches pi over 2 is equal to the function value at pi over 2. So we find the function value, we find sine pi over 2. We know that sine pi over 2 it's like the sine of 90, and the sine of 90 is 1. And so the limit as x approaches pi over 2 of sine x is 1. So again, we're thinking about continuity because we know that if it is continuous, what's true? The function value exists, and the limit exists, and the limit is equal to the function value. So by checking continuity, we know that the limit exists, and we know it's equal to the function value. So to find the limit, instead of going through some big nasty process, we just find the function value, and that's the limit. Okay? Any questions so far? All right. Let's do one more. Let's go ahead and do number 8. We know that sine is everywhere continuous, and so we can put that 7 in place of the x. And so we're going to have the sine of, I'm going to put the 7 first, 7 pi over 6, right? Now, you should know from trig to think about that 6 and say, okay, that's like 180 divided by 6 is 30. So my reference angle is 30 degrees. Remember that? So my reference is 30, so I'm thinking in my mind, okay, what is sine 30? It's 1/2. So my brain throws out a half. But we got to think about the quadrant, right? In quadrant 1, quadrant 2, quadrant 3, and quadrant 4, we have they're all positive in quadrant 1, smart. The sign only is positive in quadrant 2, trig. Tangent is positive only in quadrant 3, class. Cosine is positive only in quadrant 4. Well, we got to figure out where negative 7, 6 is. Well, this is pi, so 6 pi over 6 would be equal to pi, right? So where's 7 pi over 6 going to be? Down here in the third quadrant, where only the tangent is positive, therefore sine is negative. All right, everybody remember all of that? That's good that you remember that. Because if you didn't, it could be a while before we get good at this. Anyway, cool. So if you don't remember your basic trigonometry and your trig identities and what's positive where, you need to go back and study that. If you knew it, be sure you remember to think about it as you do that. Because if you remember in trig, you'd get the half and forget to check for what quadrant. So we can't do that in calculus either. All right. Well, we're going to stop right there, and we'll do the second half of this in a second video. Thank you.